Hi people, please stay hydrated, drink some water. I don't know why I'm saying this, but anyways, here's today's integral. It's the integral from 0 to infinity of the natural log of 1 over x cubed divided by e to the x squared times square root x dx. And yeah, let's get started. So, we'll first label this integral I, just so that we can reference it later. And to start off, we'll notice that this 1 over x here can be written as x to the minus 1. And what that allows us to do, because it's inside a log, is throw the minus 1 in front of the log, and when we cube it, it's going to become, well, negative 1. So we'll pick up a minus sign from 0 to infinity, and we'll move the stuff from the denominator to the numerator as well. So the reciprocal, we're going to pick up some minus signs here, and x to the minus a half, and that's natural log cubed x dx. And what we're going to do is compare this with the gamma function because it's really similar in structure. So the definition of the gamma function evaluated at s is the integral from 0 to infinity of e to the minus t times t to the s minus 1 dt. Now, if we compare these two integrals, we see that this part is quite similar to this part is similar to this part. Well, the dummy variables are in like the same place, but we're missing this natural log part. Now, how do we get it? We're going to get it by differentiating by s on both sides, well, with respect to s. So if we differentiate with respect to s, that's going to get us gamma prime s. And we're going to have a differential operator on this side, along with the integral. Now, can we switch up these two integrals? In this case, we can, because we're going to find out that this is going to be evaluated at s equals a quarter later on. So, because this is defined for real s greater than 0, so the stuff less than 0 is like an analytic continuation. But yeah, so we're gonna have convergence, and we're allowed to switch it up. So that's gonna be the integral from 0 to infinity of the partial with respect to s of e to the minus t to the s minus 1 dt. And e to the minus t is just a constant. When we differentiate t to the s minus 1, we're just going to multiply by natural log t dt. And yeah, so what that means is every time we differentiate by s, we're going to pick up a natural log. So if we differentiate it 2 more times, so differentiating it 2 more times, that's going to get us natural log cubed. So e to the minus t to the s minus 1, natural log cubed t dt. And so this is this is quite similar to our integral. Let me just write it down here. So our integral I is negative integral from 0 to infinity of e to the minus x squared times x to the minus a half natural log cubed x dx. And what we're going to do is perform a substitution where x squared equals t. Why? Because comparing this and this, that will allow us to get it into this form right here. So if we do x squared equals t, that means 2x dx is dt, of course, and x will be t to the half. So dx is 1/2 times x to the minus 1, which is t to the minus a half dt. So we'll just plug everything in. So that equals negative from 0 to infinity of e to the minus t times, so x to the minus a half, that's going to be t to the minus a half times a half, which is minus 1/4. So t to the minus 1/4 times natural log cubed of t to the half, there we go, times dx, which is a half t to the negative a half dt. And there's a lot of stuff we can do here. So we can first, this a half we'll throw in front of the integral. That's going to get us, well, a half cubed, that's an eighth. And combining it with this a half as well. So minus 1/16 from 0 to infinity, e to the minus t. And we'll combine these exponents right here. That's going to get us t to the minus 3/4 natural log cubed t dt. And we have it in exactly this form right now. So s minus 1 is equal to minus 3/4. That means s is a quarter. So our integral is exactly equal to negative 1/16, the third derivative of gamma evaluated at a quarter. Now, this is kind of a nice form, but there is a closed form, what I like to call a closed form, I guess. I don't know if, like, other people consider it a closed form, with, like, some special constants. So, let's see if we can give this a nice closed form. So we want to find an expression for the third derivative of the gamma function in terms of something that, well, will give us a nice closed form in terms of some special constants, I guess. So we're going to actually use the polygamma functions, which are defined as the derivatives of log of gamma. So what I mean by that is, this is the digamma function denoted by psi naught of s. That's going to be equal to the derivative with respect to s of the natural log of gamma s. And when you take the logarithmic the logarithmic derivative of some function, you're going to get the derivative of the function divided by the function itself. So what that means is the first derivative of the gamma function is digamma times gamma. And what we're going to do is differentiate on both sides with respect to s again. So gamma prime prime of s, that's going to be, using the product rule, psi 1 of s, so that is the derivative of psi 0, and it's called the trigamma function, times gamma of s, plus psi naught of s times gamma prime, but gamma prime is psi naught times gamma, so that's going to be psi naught squared times gamma. And we're going to do it again. So gamma triple prime s. So for the first part, we're going to get psi 2s times gamma s plus psi 1s times gamma prime, which is psi 1 times psi naught times gamma. And for the second part, we're going to get the derivative of psi naught squared, which is 2 psi naught times psi 1, the chain rule, and times gamma, plus psi naught squared times gamma prime, but gamma prime is psi naught times gamma, so that's going to get psi naught cubed times gamma. And yeah, so that's our little formula we're going to use. And actually, if we notice that this term is equal to this term, so we can combine that, so we can, like, destroy this and turn that coefficient into a 3, which will make life slightly better. So we are looking for, if we remember that I is negative 1/16 of the third derivative of gamma evaluated at a quarter. So we will set s equals to a quarter while factoring out gamma of s because it's present in all terms. So third derivative of gamma at a quarter, that's gamma of a quarter, which is, in fact, like, quote-unquote closed form because you can't write it in simpler terms, times psi naught cubed of 1/4 plus 3 psi naught of 1/4 psi 1 of 1/4 plus psi 2 of 1/4. So what we need is 3 values: psi naught of 1/4, psi 1 of 1/4, and psi 2 of 1/4. So let's find these one by one. So let's first find psi naught of 1/4. And what we're going to use is the kind of series representation of psi naught. So we're going to have psi naught of S is negative gamma, which is the Euler-Mascheroni constant, by the way, but I like calling it the oily macaroni constant because it's funny, plus the sum from n equals 0. Why am I laughing at my own jokes? Oh my word. Of 1 over n plus 1 minus 1 over n plus s. And if we sub in 1/4, that is going to give us what we need. So 1/4 and 1/4. What we can do to get rid of this bit, well, not get rid, but kind of write it in a better way, is multiply the sum by 4. And that will make the denominators 1 over 4n plus 4 minus 1 over 4n plus 1. That's a weird minus sign there. And how are we going to solve this? Well, we're going to use the fact that the integral from 0 to 1 of x to the 4n plus 3, because when you integrate this, forgot the dx. When we integrate this, we're going to add 1 to the thing. So it's going to be 4n plus 4. And we're putting it in the denominator. So it's going to be 1 over 4n plus 4 because, well, the bounds make the x 1. So, again, we're going to have another integral from 0 to 1 of x to the 4n dx, and that's going to give us 1 over 4n plus 1. So, if we substitute those in, we're going to get minus oily macaroni plus 4 times the sum of n equals 0 to infinity. We're going to write it as one big integral, so x to the 4n plus 3 minus x to the 4n dx. And what we're going to notice is that we can factor this as x cubed minus 1 times x to the 4n. And because it's, well, first we're going to switch the sum and integral because it's a proper integral, so it converges. So let's switch them up. And while we're doing it, we'll pull out the factor of x cubed minus 1 outside of the sum because it doesn't depend on n. And we're going to get x to the 4n, which we can write as x to the 4th to the n dx. And what we notice is that this is a quite nice geometric series because x is between 0 and 1, so x to the 4th is between 0 and 1. And so it converges, and we can use the formula. So that's going to be equal to 1 over 1 minus x to the 4th. So negative gamma plus 4 times this integral. And we're going to write this in the numerator. We're going to have 1 minus x to the 4th dx. And let's just switch up the denominator by introducing a minus sign. So a minus sign here. And let's do some factorizing. So it's going to be negative gamma minus 4 times the integral from 0 to 1 of x minus 1 times x squared plus x plus 1 divided by, let's see, x minus 1 times x plus 1 times x squared plus 1. Hope you all agree with this factorization, and we can cancel this out. So what we're left is this integral, which we are going to do some partial fractions on it. So we have this rational function that we have to integrate, and we're going to do it with partial fraction decomposition. because of course that's like the most rational way to do it. Stop laughing at your own jokes, Joe. Oh my word. Okay, anyways, this is going to be equal to a over x plus 1 plus bx over bx plus c divided by x squared plus 1. And multiplying everything by, well, x plus 1 times x squared plus 1, of course. We're going to get a times x squared plus 1 plus bx plus c times x plus 1. And we're just going to compare coefficients because polynomials are elements of a vector space, and these are like basis vectors. Anyways, I don't know what I'm talking about at this point. So, comparing coefficients, x squared it has a coefficient of 1. And also, I just realized, very sorry, that should be a plus right there. Why did I write minus? I don't know. Anyways, that should be plus. And comparing coefficients, the coefficient for x squared is 1. And so 1 is, well, let's see. There's an a here. There's a bx squared. So a plus b. The coefficient for x is, well, it doesn't have an a. It has a b and has a c. So b plus c. And the constant coefficient, the constant term, is a plus c. And we can see that this clearly means that a plus b, not a plus b, oh my word, a equals b equals c equals a half. So all of these are a half, and when we plug them back into the partial decomposition, we're going to get 1 half divided by x plus 1, which is, well, we're going to put that in the denominator actually. So 1 over 2 x plus 1 plus, and we're going to factor out a half. So that's going to be x plus 1 divided by 2 times x squared plus 1, I believe. Yes, we factored out, like, because b and c are both a half, we factored it out and put it in the denominator. And we're going to have to integrate it from 0 to 1, multiply it by 4, and minus gamma, something stuff. So integrate it from 0 to 1, minus gamma, minus 4. I don't know why it's so far left, but oh well, who cares? So that is what we're going to have to integrate. So we're going to split it up into 2 integrals. So a half times x plus 1 dx plus, should we do a half as well? Let's do a half. Times integral x plus 1, oh my word, yeah, x plus 1 divided by x squared plus 1 dx. And because we have an x squared plus 1 at the bottom, let's multiply the top by 2, which will make this a 4 actually, because we want the derivative to be at the top. So 2x plus 2, and let's split this up again. So don't forget the factor of a quarter. That would be 2 x squared plus 1 dx. Now, integrating all of this, the first integral is a half times natural log of x plus 1, evaluated at 0 and 1. 0 is going to get us natural log of 1, which is 0. Plugging in 1 is going to get us 2, so natural log of 2. Plus, let's see, a quarter times natural log of x squared plus 1, evaluated at 0 and 1, which is, again, plugging in 0 is going to get us 0, plugging in 1 is going to get us 2, so 2, natural log of 2. And, let's see, plus a quarter times 2, so that's going to be a half times arctangent of x, evaluated at 0 and 1. So 0 is going to get us 0, 1 is going to get us pi over 4, so we're going to have pi over 8 pi over 4 times a half is pi over 8. Yep, there we go. And distributing the 4 in is going to get us minus gamma minus 2 natural log 2 minus natural log 2, so that's minus 3 natural log 2 minus pi over 2. So that is our value for psi naught of a quarter. Maybe we should move it in a bit. So this is our value we're looking for, psi naught of a quarter. And so let's find the next one. So let's find psi 1 of a quarter now. And the way we're going to do this is we're going to find a relationship between psi 1. Should we use red this time? Oh my word. Psi 1 of... Come on. Where's my pen gone? Okay. Psi 1 of 1 minus s and psi 1 of s, because there's a reflection formula that tells us that psi 1 of 1 minus s plus psi 1 of z is equal to pi squared times cosecant squared pi s. Sorry, I'm used to using z in these cases because complex, but anyways, pi z. So when we plug in a quarter, we're going to get a relationship between psi 1 of a quarter and psi 1 of 3/4. And when we plug in a quarter for s on the right, we're going to get cosecant squared of pi over 4. So sine of pi over 4 is root 2 on 2. Reciprocal, that's root 2, I believe. Yep, root 2. And squared is 2. So that's going to get us 2 pi squared. There we go. And to find psi 1 of 1/4 kind of indirectly, we're going to consider this relationship as well. Psi 1 of 1/4, same thing, minus psi 1 of 3/4. And what we're going to use is actually the series representations of these things. So, should I write it here? So, psi 1 of s, that can be written as the sum from n equals 0 to infinity of 1 over n plus s squared. And that's really convenient because we can just put it in. So, and we're going to combine the sums as well, actually. So n equals 0, 1 over n plus a quarter squared minus 1 over n plus 3/4 squared. And what we're going to do is multiply the sum by 16. That will, it's similar to like the sine naught part, so that will change this denominator into 4n plus 1, yep, and that into 4n plus 3. And what we're going to notice is that these are the integers 1 mod 4, these are the integers 3 mod 4, so they're just the odd integers really, but they alternate in sign. So that's going to be equal to 16 times n equals 0, the reciprocal of the odd integers squared, but alternating in sign. So alternating in sign, that's minus 1 over n, the odd integers squared. And what we notice is that this sum quantity is exactly equal to g, which is called Catalan's constant. And it pops up everywhere when you're doing like these integrals of this type. So that's going to be 16g. And if you add the two equations together, that's going to get us 2 times psi of 1 over a quarter, and the psi of 3/4 cancels out. That will equal 2 pi squared plus 16g. And therefore, psi 1 over a quarter is equal to pi squared plus 8g. There we go. That's psi 1 over a quarter. There's one left until we can plug everything in. So let's find that one as well. So psi 2 over a quarter. We're getting close now. And we're going to use quite a similar approach to psi 1 over a quarter. and we're actually going to consider the reflection formula which we just used. So this is the reflection formula we used. That's equal to pi squared cosecant squared pi s. Now, if we take the derivative of this formula, because the derivative of psi 1 is psi 2, we're going to get a reflection formula for psi 2. So, derivative of psi 1 of 1 minus s is going to be psi 2 of 1 minus s. But we're going to pick up a minus sign because chain rule. Plus psi 2 of s. That equals pi squared is a constant. It's a coefficient. It's a constant factor. And the derivative of cosecant squared pi s, we're going to spam the chain rule. So that's going to be 2 cosecant pi s times negative cotangent pi s cosecant pi s times pi, because of the pi s. And if we plug in a quarter, that's going to give us negative pi psi 2 of 3/4 plus psi 2 of a quarter is equal to, let's see, we're going to get a negative 2 pi cubed out front and a cosecant squared pi s cotangent pi s. Cosecant squared pi s, we know that's 2 from the previous calculation. And cotangent pi s, well, tangent pi over 4 is 1. Reciprocal is 1, so that's just gone. So all in all, that's 4 pi cubed, right? And similarly, we're going to do the same thing, but we're going to use the series representation of psi 2. So we're going to consider, because this is a minus sign here, we're going to consider psi 2 of a quarter plus psi 2 of 3/4, so we can cancel that out. And the series for psi 2 is psi 2 of s is negative 2 times the sum from n equals 0 to infinity of 1 over n plus s cubed. So let's just plug that in. And let's bring out the minus 2 out front as well. So sum n equals 0 to infinity 1 over n plus a quarter cubed plus n plus 3/4 cubed. And we can multiply the sum, again, by 64 this time, because 4 cubed is 64, to get rid of the denominator fraction. So 128, that's going to get us 4n plus 1 cubed, 4n plus 3 cubed. And what we notice is that this is 1 mod 4, this is 3 mod 4, so it's still the integers, it's still the odd integers. So that's going to be 2n plus 1 cubed. And this is awfully similar to the Riemann zeta function evaluated at 3. So let's consider that and see if we can get anything out of it. So the Riemann zeta function evaluated at 3 has this sum, has this representation. And if we change n to 2n, if we consider only the the even numbers cubed, the reciprocal of the even number cubed, factoring out a half cubed, that's going to get us an eighth, times the sum of 1 over n cubed, so that's an eighth of zeta 3, and these are the odd numbers, so all the numbers minus the even numbers, sorry, these are the even numbers, I keep saying they're odd, all the numbers minus the even numbers gives us the odd numbers, so that's going to get us 1 minus an eighth, which is 7/8 of zeta 3. So this is exactly minus 1 to 8 times 7/8 zeta 3. And 1 to 8 divided by 8, that should be 16. 16 times 7 is 112. So that's negative 112 zeta 3. And if we add these two equations together, we're going to get, well, let's see. These two cancel out. So 2 side 2 of a quarter is going to be equal to negative 4 pi cubed minus 112 zeta 3. Dividing my 2 on both sides. Side 2 of a quarter is negative 2 pi cubed minus 56 zeta 3. There we go. We've got all the polygamma functions we need evaluated at a quarter. Let's sub everything back in then. So we're going to recall that we derived these expressions earlier, and now we're ready to plug everything back in. So we're going to use, well, we just derived that sine naught of a quarter. That's minus gamma minus 3 natural log 2 minus pi over 2. Psi 1 of a quarter is pi squared plus 8g. And psi 2 of a quarter is negative 2 pi cubed minus 56 zeta 3. Therefore, our original integral I is, let's write that down as well. So the integral, that is a crowbar, an integral from 0 to infinity of natural log cubed 1 over x divided by e to the x squared root x dx is equal to, let's see, negative 1/16 of gamma of a quarter, let's write that bracket a bit better, times psi naught cubed. So psi naught is negative gamma minus 3 natural log 2 minus pi over 2 cubed plus 3 psi naught, negative gamma minus 3 natural log 2 minus pi over 2 times psi 1, pi squared plus 8g, and plus psi 2 of a quarter. So plus negative 2 pi cubed minus 56 zeta 3. And are there enough brackets? Right, so we also have this minus sign in front, which will help distribute everything back into positiveness. So distributing it into this term here, that's going to make everything inside positive because of the cube. Yep. Let's put that bracket a little closer, shall we? There we go. And distributing it into this term, that's going to make everything positive. And distributing it into this term, it's going to make these positive. So that's going to get us plus 2 pi cubed plus 56 zeta 3. By the way, zeta 3 is called Apres constant. Just as a side note. And G is called Catalan's constant. I don't know if I said that. So, anyways, this is the final form. Yeah, this is the final closed form. And I hope you enjoyed it. It's quite a tedious derivation. Let's put this in a box, by the way. Just because it's nice to put stuff in boxes, right? Yeah. Oh my word, I just deleted the box. There we go. Yeah. Hope you enjoyed this. See you soon.